In section 7.5, we will be looking at the transformations of quadratics, and we'll actually kind of look at the transformations of several different types of graphs. But before we can look at those, we have to know about what we call the parent graph for a quadratic. So that is your most basic quadratic that you can have, which is just y equals x squared. So any function we can graph by simply just plugging in numbers and plotting those points. So if we do that here, if we just pick some numbers to use like -3, -2, -1, 0, 1, 2, 3, we can get some points that we can plot here. So if we plug -3 into this equation, -3 squared would be +9. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So we can plot these points here. So we would have the point -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So we would have this shape of this parabola right here. This is our parent graph that we start with when we graph any quadratic. Now, this same method works on any problem. So for example 2, I'm going to graph y equals x squared minus 3. It's always an option just to plug in the numbers. So we could do the same thing we did on the last problem. We would have -3, -2, -1, 0, 1, 2, 3. I could use other numbers here, but this will give me a pretty good picture. So if I plug these numbers into my equation, y equals x squared minus 3, I would have -3 squared minus 3. That's going to give me 9 minus 3, which will be 6. Then I would have -2 squared minus 3. That's 4 minus 3, which is 1. I would have -1 squared minus 3, which would give me 1 minus 3, so I get -2 here. I'd have 0 squared minus 3, which is 0 minus 3, so that'll give me -3. Now, notice as I start plugging in these positive numbers, 1, 2, and 3, it's not going to change much about the results that I'm getting. So like if this -1 here was a +1 instead, I'd still get 1 minus 3. So this is going to be -2. I'll have a +1 here for that answer, and I'll have a 6 here. So you'll notice these graphs are symmetric and the numbers will tend to repeat. So if we plot these points, we've got -3, 6, -2, 1, 1, -2, 0, -3, and then those points are mirrored on the other side of the y-axis. And that gives us the graph that we see here. Now you should notice that this looks exactly like the graph that we had before, except for it's been slid down 3 units. It can be very cumbersome to have to plug the numbers into all of these equations, especially if it is a more difficult equation. So what we're going to learn about today is how we can tell what a graph will look like even before we actually plug in the points. We can tell what the graph will look like so that we could graph it in a much quicker fashion. So let's look at what that will look like from the equations here. So the first thing we're going to talk about is a vertical translation. When a function is moved up or down, that we call that a vertical translation. And as we saw in the last problem, when we put that -3 on the end, it moved the problem down 3, or moved the graph down 3. So here we'll have, if we have f of x plus a number k, assuming here that k is greater than 0, that'll move the function up k units. And if we subtract k, that'll move the function down k units. So, if we look at these examples that we have here, when I see y equals x squared minus 5, I know that this is a quadratic because I can tell that it has this x squared right here. And then I see this -5 on the end. That tells me that this graph has been moved down 5. So I would start with that parent quadratic function, and I would move it down 5 units. Example 4 is going to be another quadratic, but this one is going to be moved up 8 units. This one might throw you off a little bit because that 8 is in the front, We could always rewrite this one to make it look like this, x squared plus 8, and that would tell us that the quadratic has been moved up 8. Example 5 is different because it's not a quadratic. Whenever I see this 2 to the x power, that tells me that this is an exponential function. The 2 here does not actually do anything to the graph. It just makes what we start with look a little bit different. So we'll have an exponential function here, and that plus 9 tells us that the exponential function has been moved up 9 units. Number 6 does not even have, we don't know what type of function we're dealing with. We just see f of x. So I would just call this a function, and that minus 7 tells me that it's been moved down 7. For example 7, I have another exponential. This is a different exponential than the one we saw in example 5, but we're still just going to call it an exponential. And that 12 right there is going to move it up 12 because it is a positive 12. Just like number 4, we could switch that around and make it y equals 3 to the x plus 12 if that helps us look at this a little bit better. So we can move a function up or down simply by adding a number to the end of the function. Now, let's look at these graphs here on the calculator. I'm going to pull up a Desmos graph. It actually already has these graphs for us. Here, let's see. I'll make these go away for a second. So the red graph here is y equals x squared. Whenever I put the blue graph up here, we see y equals x plus 3 squared. Notice this time the graph did not move up or down, but it moved left or right. In this case, I added 3, and it moved the graph to the left 3. That might be the opposite of what you would think would happen, but putting that plus 3 inside of the parentheses is going to move the graph in the opposite direction. Rather than going to the right 3, as you would expect, it moves to the left 3. Whenever we look at x minus 5 squared, we can see here that this time the graph is moved to the right 5 units. Again, it's the opposite. We have a minus 5, it moves to the right or positive direction 5. So whenever we are looking at horizontal translations, it is the opposite of the sign that we see inside of the parentheses. So if I have x plus k here, it's going to move the graph to the left k units. And if I see x minus k, it's going to move the graph to the right k units. So let's look at some examples here. And we're to describe each transformation. So when I see x minus 9 squared, the squared on the outside tells me that I'm dealing with a quadratic. And the minus 9 on the inside, because it's on the inside of the parentheses, I know that it moves the graph to the left or right. And whatever's on the inside of the parentheses goes in the opposite direction. So the minus 9 here makes me think that it goes to the left, but it does not. It's opposite direction, so it will go right 9. Example 9, this is a quadratic that is going to be moved to the left 1. Now, I've thrown in some other examples here. So for example 10, I've got a quadratic again because of that square. But this minus 5 is not in the parentheses, so this is going to move the graph down 5. With exponentials, it's going to look a little bit different. There are not any parentheses, but as we see in example 11, we have an exponential function here, and we don't see parentheses, but our x plus 3, both of those are up in the exponent together, so it's like they have parentheses around them. So this plus 3 that's added inside of the exponent there is going to move this graph to the left 3. Example 12 has a couple different things going on. We're still dealing with a quadratic here. The minus 4 on the inside of the parentheses is going to move that quadratic to the right 4. but the minus 3 on the outside of the parentheses moves the quadratic down 3. So we actually see two different transformations that occur here. Example 13 is another problem where we just have function notation. We don't have the actual equation of the graph. So this would be just a function. And this minus 2 is on the inside of the parentheses, so it's a function that's been moved to the right 2. Then for example 14, we're going to see a function that has been moved to the left 3, the opposite of the sign inside of the parentheses, and then up 5. So we have a couple transformations that have happened there. We have one more thing that we need to look at. So let's go back to a graph here, and we're looking at this, and let's get rid of these graphs. So we've got y equals x squared. Let's look at what happens if we put a negative in front of that x squared. You see what happens to the graph here? It flips the graph upside down. In a similar fashion, if I had something like we see here, x minus 4 squared, if I put that x minus 4 here, see how that moves to the right 4. If I type here negative x minus 4, now see that that graph also is flipped over the x-axis. Now if I have a graph like this, y equals x squared plus 5, that's our normal quadratic moved up 5. And I also graph, as you see here, negative x squared plus 5. Notice that this graph has been flipped upside down. Now this time, the graph doesn't look like it's been flipped over the x-axis. It's been flipped right there at that vertex, but what has happened is it's been flipped first and then moved up 5. So let's do some let's talk about this in general. A reflection over the x-axis, if we have a negative out front of the function, it's going to reflect that graph over the x-axis. Reflections take place before any translation, so that's why whenever we look at this graph, what happened here is we had y equals x squared. Let's get rid of these two. We started with this y equals x squared. We flipped it over the y-axis first, and then we moved it up 5 by putting that plus 5 on the end. So let's look at these last few examples. Whenever I see a problem like y equals 10 minus x squared, I first know it's a quadratic because of the square. And because I see a negative in front of that x squared, I know that this graph has been reflected over the x-axis. Now this 10 out here, this is a positive 10, and it is not inside of any parentheses. It's added to that negative x squared. So this quadratic has also been moved up 10. Another way you might see this written is y equals negative x squared plus 10. That looks a little more like what we're kind of used to seeing. For example 17, I have another quadratic. This one has a negative out front, so it has also been reflected over the x-axis. And this time I have a minus 4 inside of the parentheses, so this quadratic has been moved to the right 4 units. For example 18, this time I just have a function. Don't know what it looks like, but it's some sort of function. That negative out in front of the function tells me that it's been reflected over the x-axis. And then I have this plus 7. It's on the end. It's not inside of the parentheses, so that tells me that the function is moved up 7 units. Our last one may seem a little bit tricky. It might be helpful to move this 9 sort of to the end and write it like this: y equals negative x plus 3 squared plus 9. Just move that positive 9 there to the end. So here we have a quadratic. That negative tells me that it is reflected over the x-axis. The positive 3 on the inside of the parentheses tells me that the graph has moved left 3. And the positive 9 on the end tells me that the graph has moved up 9. So this can all be very helpful if we need to think of what a picture of the graph looks like without actually graphing it. Whenever you get to sort of your upper level math, this will be a major concept that you'll focus on. So this is sort of an introduction that we're seeing.